4.5 Electromagnetic Effects Memo. Question 1. A coil of wire is connected to a voltmeter. A magnet is moved towards the coil of wire and a peak voltage of 0.25 volts is observed. A. How could the motion of the magnet be changed to increase the peak voltage observed? Well, simply move the magnet towards the coil faster and you are going to increase the peak voltage. B. How could the motion of the magnet be changed in order to change the direction of the voltage observed? Well, simply move the magnet in the opposite direction and it will change the polarity of the voltage. Number 2, explain the use of slip rings in the alternating current generator. Well, the slip rings allow the wire to turn around or to turn as the generator rotates without coiling up and being tangled up. 3, a wire is placed on a magnetic field as seen below. So when a switch is closed, which direction will the wire between the magnetic poles experience a force? Well, the force is going to be upwards, and let me explain why. So using Fleming's left-hand rule, the magnetic field is going from north to south, so to the right. The current is coming out towards us because of the direction of the cell. So by using Fleming's left-hand rule, the force is going to be upwards. Both the magnetic field and the current direction are now reversed. Which direction will the wire experience the force now? Well, it's going to be exactly the same direction. If you change the magnetic field or the current direction, the direction of the force is reversed, but by reversing both of them, actually we end up in just the same direction. Draw the magnetic field observed around the wire XY when the switch is closed. So using the right-hand corkscrew rule, if you grip the current, the conventional current is going from Y to X. So by using the grip rule, it's going to go around in the direction seen in the picture. Number 5, the diagram below shows a beam of protons, which are positively charged, being fired into a magnetic field that's perpendicular to the proton's direction of motion. Determine the direction of the protons will experience a force and sketch the path within the field. We've got the proton stream. Well, if the magnetic field is going into the page, again, using Fleming's left-hand rule, initially, as they go in, the force is going to be upwards. That's going to cause the motion or the path to change, and then the force is always going to be at right angles to the direction of motion. So initially the force is upwards, as we're looking at from the paper, but that's going to cause a corkscrewing kind of effect, rotating around a single point. Number 6, state 3 changes you can make to a direct current motor to increase the motor's turning effect. Well, you can increase the current, you can increase the magnetic field strength, or you can increase the number of turns on the coil. And then how can the direction of a DC motor rotation be reversed? Well, you can actually just reverse the direction of the electric current. 7, a transformer has an efficiency of 100%. It has 200 turns on the primary and 1,000 turns on the secondary. With a 12 volts AC supply connected to the primary, well, what's the voltage measured across the secondary coil? Well, it's a 200 to 1000 ratio, which is 1 to 5 ratio. So 12 times by 5 is going to be 60 volts. B, a current of 2 amps is measured entering the primary coil. How would the current be measured, or what would be the current measured on the secondary coil? Now this time the ratio is reversed. So for the same increase in current, we get the same decrease. For the same increase in voltage, we get the same decrease in current. So if it was a 1 to 5 ratio for voltage, it's now going to be a 5 to 1 ratio for current. So 2 divided by 5, I get 0.4 amps. The 12 volt AC source is now replaced with a 9 volt DC source. Hopefully you noticed that. What would the voltage on the secondary now be, and why? Well, it would be 0. Because the magnetic field in the primary is now stable, okay, and it will not induce an EMF in the secondary. Remember, the magnetic field has to be changing in order to induce an EMF. Okay, 8. A light bulb has a resistance of 36 ohms and a current rating of 2 amps. How much energy is transferred if the bulb is left on for 90 minutes. So we're actually going to use this equation, P equals I squared R. So I squared, you're going to be 2 times 2 times by the resistance of 36, and I get 144 watts. And then the work done is power times by time. Remember, we've got 90 minutes, so we need to convert that into seconds. So 144 times 90 times 60. Well, we get, in an unrounded form, 777,600 joules. So rounding up to 2 significant figures, we get 780,000 joules. Finally, number 9, the UK's national electrical grid conveys electricity at a voltage of 400,000 volts, a huge voltage. Outline the main reason for such a high voltage being used. Okay, well, it comes down to this equation, P equals I times by V. By increasing the voltage of the grid, you need a much smaller electrical current for the same amount of power. Now, the problem with current in wires is that it causes unwanted heating, and that will make the system inefficient because basically you're heating the environment, some field with a load of cows getting heated. It's not really a very useful use of your energy. All right.